Okay, let's take a look at something called the conservation of quantum probability, or the continuity equation of the probability density functions. I got this from, I want to give credit to where credit is due, the Mathematical Principles of Quantum Mechanics by Derek F. Lawden. This is on page 116. I added a few steps to make it a little bit more understandable. He expects you to be a little bit smarter in mathematics, so I added a few steps to make it easier to understand. This is Schrodinger's equation, time dependent, multiplied of an imaginary wave function here, multiplied by the conjugate of that wave function. So I multiplied it here, the conjugate, and the conjugate. So this is just Schrodinger's equation with the conjugate wave function multiplied through. This is Schrodinger's equation again for the conjugate particle. So notice the conjugate wave function is here. And I've multiplied that through, or Mr. Lawden, Professor Lawden, has multiplied that through by just a regular wave, the regular wave function, or the conjugate, if you will, of the conjugate wave function here. So this is just Schrodinger's equation, and Schrodinger's equation is multiplied by the conjugate and multiplied by the Schrodinger's equation of the wave function multiplied by the conjugate of the wave function, and the Schrodinger's equation of the conjugate wave function multiplied by the wave function. And we're going to subtract these two equations. And when you do that in a little bit of algebra, you'll get this. When you subtract this will become positive, and this will be a product rule right here. So I wrote it as the derivative of the two functions multiplied. Okay? So I did a little bit of a step in my head there. There's an identity for del. Del some function, del some other function, is equal to the wave function, del squared, the second function, if you will, plus del the second function, del the first function there. That's an identity. Why don't we scoot this guy over? So there he is right there. That's there, and that's there. And we'll write this out for this term, and then we're going to switch these two and make this conjugate, and this is just a regular wave function. And if we did the same thing for this equation, obviously, well, we could just take this equation and just switch the wave function to the conjugate wave function. So wave function, conjugate wave function, conjugate wave function. Don't worry about that. I scratched that out. Wave function, conjugate, wave function, conjugate wave function, conjugate wave function, wave function. So obviously we just switch the two functions here. So we have this equation and this equation, and we're going to subtract these two equations. And when we subtract these two equations, these two terms will cancel out. So we'll have this minus this, which is here if I pull the del out. And then we'll have this minus this, which is this right here. Well, I don't know if you recognize this, but he's sitting right over here. So in for this, this equation says we can put all this in. So we're going to put all of this stuff in here. This will stay the same, but this will change to all this stuff pumped into there. Okay, so here we go. Remember the h bar squared over 2m, then it's going to be this thing equals this. That's going to be on the next page. There it is. Well, by the way, we could, of course, cancel the... there was an h bar squared and an h here, so we could cancel the h bar. So we're going to end up with not an h bar squared, but just an h bar over 2m del this, like I told you we were, and then this stayed the same from the page previously. Let's define the probability current density vector to be this, J equals this, and we'll define the probability density rho equal to psi times the conjugate of psi. Okay. Well, if we define these two this way, then of course this is sitting right there and there. So we'll get del J, which is right here. We'll scoot over the I just for the hell of it. We'll scoot over the I over here. So it'll become here. It'll go on top and become negative. So that when we rewrite this as the partial of rho, which is this stuff, so you have the partial of rho, partial with respect to t. That was on this side, so when we scoot it over, it'll become negative. But because we put the I had to put the I on the bottom here. When it comes upstairs, it'll be positive I, and it'll become negative I, and when you multiply through by a negative, this will become negative, which means when you scoot this over, it will become positive here. Hopefully you followed that. Anyways, the algebra is correct here. If you do the algebra, you'll get this. Okay, so what is this right here? Well, we call this the probability equation of, or the equation of probability continuity for the particle. We can also rewrite this way, which means I should have just left it like this. Might be a little bit easier to interpret into an English sentence. And that is that, I'll read it out for you. The flux of J outward across a closed surface S is the rate, partial, at which the probability of finding the particle inside the closed surface S is decreasing because of the negative right there. Okay? So, anyways, it's a neat way to interpret the probability that of finding a particle inside a surface S there. Okay, I hope you enjoyed this video. I look forward to any comments at the bottom. Thank you for watching.